Welcome back to the Mathematics 23 review slides by UP Mathematics Club. In this video, we will be discussing problems involving parametric surfaces and surfaces of revolution. Here's the idea. A surface is generated whenever we revolve a radius function r in two variables about one of the axes of the x, y, and z plane. This GIF shows how it works. Now, let's take a look at some problem examples. Here, we need to identify the parametric surface given by the vector valued function r by finding its corresponding Cartesian equation. For the solution, the parametric equations of the surface are x is equal to r cosine theta, y is equal to r sine theta, and z is equal to 3r. We get this parametric equation by equating the vector components of the vector valued function r to the x, y, and z coordinates correspondingly. After that, eliminating r and theta, we get x squared plus y squared is equal to r cosine theta squared plus r sine theta squared. Factoring out r squared, we get r squared multiplied by sine squared theta plus cosine squared theta. Now, sine squared theta plus cosine squared theta is equal to 1. So, we get x squared plus y squared is equal to r squared. Substituting the value of r from this equation, we get x squared plus y squared is equal to z over 3 squared. Simplifying this equation, we get 9x squared plus 9y squared is equal to z squared. Thus, the given parametric surface is a spherical cone. Moving on to problems involving parametric surfaces. Here, we need to find an equation of the tangent plane and the normal line of the surface defined by the position vector function r at the point 135. We do that first by looking for the unique ordered pair uv that gives the point 135. And we get that by solving this system of equation that we got by equating the vector components to the x, y, and z coordinates correspondingly. Adding x and z will give us u is equal to 2. Therefore, v is equal to 1. This can be verified by substituting u and v to y. Then, we need to compute for the partial derivative of r with respect to u and the partial derivative of r with respect to v. For the partial derivative of r with respect to u, we get 1, 2u, 2. Substituting the values of uv, we get the partial derivative of r with respect to u is equal to 1, 4, 2. Then, computing for the partial derivative of v, by the same process, we get -1, -2, 1. Now, these two vectors are not necessarily perpendicular to each other, but they are both tangential to the surface at point 135. So, taking the cross product of these two vectors, we get a normal vector to the surface S at point 135, which is 8, -3, 2. Thus, the normal line to the surface S at point 135 is given by this vector. Moreover, the equation of the tangent plane to S at the point 135 is 8 times x minus 1 minus 3 times y minus 3 plus 2 times z minus 5 is equal to 0. And that is all for this video, guys. See you on the next one.